Hello everyone, my name's Luke Daly and I'm a lecturer in the School of Geographical and Earth Sciences at the University of Glasgow. And in this week's talk we're going to be exploring how the Earth became the habitable world we see today. So planet Earth is a really special place. In fact, in our solar system it's almost unique. It's the only planet that has liquid water stable at the surface, and also the only planet, so far as we know, that has life on it. If you look at our neighbours, Venus is a vision of hell. At the surface temperatures melt lead and it rains sulfuric acid. Going out further, Mars, much smaller than the Earth, it's lost most of its atmosphere to space and is a bone-dry, cold desert planet. But believe it or not, Earth may not have always been this beautiful blue planet. In fact, when it first started, it might have been a dry desert world. And this is because of something called the snow line. Now, I want you to pay attention here because this is very complicated science. The sun is hot. And so in the inner solar system, all the gas and dust that's swirling around the young sun and any water that's there will be heated up so much it will boil and become a vapor. In the outer solar system, where it's really cold away from the sun, all that water vapor will condense down to ice and be solid. Now what that means is that early young energetic sun will blow that water vapor out into the outer solar system and we lose it from the inner solar system. So our poor young Earth is forming in that inner solar system and doesn't have any water to form with. So we think the Earth formed dry. However, even if by some mechanism we could get some water into that young proto-Earth, we would also lose it almost immediately in the cataclysmic impact between a Mars-sized planet called Theia impacting with the Earth to form the Moon. That will generate a global magma ocean completely melting the Earth, and any water that it started with would be quickly boiled off into space. So the key question is, how did that change? I'm currently standing in Glasgow. You can see the lovely river behind me. It rains here all the time. Clearly our planet has changed somewhat from its dry beginnings into a world that's full of water and able to support life. So where did Earth's oceans come from? We think it must have come from space in the far reaches of our solar system. And the way we try and figure that out is by measuring the deuterium-hydrogen ratio. Now water is made up of hydrogen and oxygen, and that hydrogen can come in two forms, hydrogen or deuterium. Hydrogen is just one proton, whereas deuterium is that one proton but with an extra neutron. So it's like one heavier than hydrogen. And the ratio between that can tell us where an object formed in our solar system and kind of acts as a watery fingerprint of extraterrestrial objects' water reservoirs. So we can look out into our solar system and try and figure out what reservoirs of water could have added to the Earth to produce Earth's deuterium-hydrogen ratio. Now, when we look out at all the water-rich objects in our solar system, there's one clear, obvious frontrunner that everyone thinks about when they think of water delivery, and that's comets. Big, dirty snowballs, chock full of water, and also chock full of organic material. Basically everything a growing planet needs to be a habitable world on which life could emerge. However, we've been good little scientists and we've gone and measured a bunch of these comets, and their deuterium-hydrogen ratio is off the chart. It's really heavy, has loads of deuterium, and looks nothing like what we see on Earth. So they're kind of ruled out. We can't really add any comets, which is then a problem. We then look a bit closer to home in the asteroid belt and we find these water-rich asteroids, and they are great. We have samples of them on Earth in the form of meteorites, and when we measure their deuterium-hydrogen ratio, they're really close to the Earth. They're almost identical. So actually, these water-rich asteroids being close to the Earth is a good thing. They could provide some of Earth's water. However, they form in the outer solar system, beyond that snow line that I mentioned before. And so there's a challenge. How do you get them into the inner solar system to hit the Earth as it's forming? And this brings me to one of my favourite theories in planetary science called the Grand Tack hypothesis, which is basically throw Jupiter at all your problems and hope they go away. So Jupiter, we think, formed early in our solar system, and it slowly migrated inwards towards our young sun. What the effect that had is nicked loads of Mars's stuff, and that's why Mars is really small, and it could have gone all the way through and destroyed all the forming terrestrial planets. But fortunately for us, Saturn also formed, and then basically dragged Jupiter back by the scruff of its neck all the way back out into the outer solar system where it finds itself today. That's good for us, so it means we still had a chance to form as the early Earth, but also would destabilize all the icy bodies in the outer solar system and send them slinging into the inner solar system, turning the inner solar system into a pinball machine, and lots of those water-rich asteroids would come slamming into the Earth, delivering some of Earth's oceans. And that's a great theory, that works really well. However, I said almost before, they almost match the Earth's deuterium-hydrogen ratio. They are in fact slightly heavier. And this brings us to the problem graph in planetary science. So the Earth is kind of moderately heavy in deuterium and hydrogen. However, when we look at comets, like I said, they're off the scale, they're way higher. Water-rich asteroids are similar, but on average slightly heavier. And indeed, any water-rich object that we've gone and measured so far in our solar system has been heavier than the Earth. And that's a problem because you can't mix three heavy things and get a lighter thing. We need something on the other side of the graph to balance this book, to provide a light isotope ratio of water. The reason this graph's a problem is the only object on the other side of the graph with appreciable hydrogen or water in it is the Sun. Now, I'm not going to suggest we throw the Sun at the Earth, because that would be bad for everybody involved, but the Sun might present an unusual out-of-the-box solution to our problem graph, and that is through a process called space weathering. Now, space weathering is the combination of the Sun's solar wind, which is a stream of hydrogen ions and helium ions, as well as ultraviolet radiation, alongside micrometeorite impacts that come zipping in and impacting planetary surfaces, and galactic cosmic rays, which are these high energetic particles produced in the death of giant stars. These processes bake and irradiate the surfaces of any world exposed to the vacuum of space. So that's like things like the surfaces of comets, the surface of Mercury, the surface of the moon, billionaire's car apparently, and also the surfaces of asteroids and the tiny dust grains that are on those surfaces. And that brings me to one of my favourite equations in planetary science. Basically, the Sun's solar wind produces a stream of hydrogen ions, or protons. You add those to rocks, and you generate water in their outer surface, as that hydrogen comes in and nicks oxygen out of the crystal structure, producing OH and eventually H2O. This produces a thin 200 nanometer wide layer of water on the surface of asteroids that is produced purely by the solar wind. However, how much water you can put in there was an open question, and that's what we've attempted to do to try and address some of these questions. We got given 3 whole particles from the asteroid Itokawa that was brought back to Earth by the Japanese Space Agency's Hayabusa mission. These particles were all about the width of a human hair, and another unaccounted for reservoir of Earth's water is the sweat from my brow and the stress of trying to pick up these tiny, tiny dust particles. However, we managed to successfully mount them and put them in an incredible machine called an atom probe, which literally tears apart your material one atom at a time. And it's one of the few ways we can see this water and visualize it in 3D in such a small volume. What we found was really exciting. We saw this outer layer of water. So these tiny dust grains can have about 1% by mass of water locked in them from the Sun's solar wind. That equates to about 20 litres of water per meter cubed of asteroid or lunar regolith, which is a lot, which is really important actually if you think about it, because that's then a renewable resource of water on the surfaces of airless worlds, which will be vital if humanity wants to put people back on the moon, and will provide a renewable, clean source of water, not only for those astronauts to drink, but also to, split into oxygen and hydrogen to produce rocket fuel. But back to the Earth. What do tiny dust grains irradiated by the Sun's solar wind have to do with solving the problem graph of Earth's oceans? When we look into our skies at what's raining down on us all the time, about 50,000 tons of material hits the Earth every year. Meteorites, fist-sized objects, make up almost none of that material. Bigger-sized objects like comets and asteroids, fortunately, are very rare, but when they do hit us, can maybe contribute about 1% of that 50,000 tons. But by far and away, the biggest contributor by mass are those tiny wee dust grains that are irradiated by the Sun's solar wind. And that is true to right now, today, and also true when the young Earth was forming. So that material, enriched in the Sun's solar wind, which is isotopically light in hydrogen from the Sun, could be an additional reservoir. And in fact, when we model the contributions of water-rich asteroids and irradiated dust particles to the Earth, about a 50-50 ratio of dust grains to water-rich asteroids is enough to explain Earth's hydrogen isotope composition. Or as I like to think about it, half a glass of sunshine in every glass of water, as an extra bit of motivation to get your 2 litres the doctor says you should drink of water per day. So I think that's really cool. However, what's even cooler is I'd like to leave you with this thought. When you are standing on the early Earth, you would be standing on a dry desert world. but you would be seeing this beautiful display of large water-rich asteroids raining down, as well as the most spectacular shooting star display of those tiny dust grains literally raining water into Earth's atmosphere, starting to produce that beautiful habitable world. And this would not be a unique process to the Earth. It should happen on Venus and Mars. They should also have got water this way. In addition, it should have happened to any terrestrial planet across the galaxy. So delivering water to a terrestrial planet might not be the prerequisite for life that we think it is. A more important question might be, how do planets hold on to that water for long enough for life to emerge on them? So thanks very much for listening. And if you've enjoyed what you've seen and heard and learnt about today, do consider coming to the University of Glasgow in the School of Geographical and Earth Science to do one of our geology, environmental geoscience or geography degrees. Thanks very much.